We've been discussing double displacement reactions in the last couple of chapters, so today we're going to do a double displacement experiment. We have 15 different chemicals that we're going to be working with today, and we're going to do 14 different combinations. For example, the first reaction in the lab today will be combining silver nitrate and sodium chloride. You'll be writing out the chemical equations for each of these 14 reactions. This lab is also a bit complicated, so I have a fairly complete pre-lab that I'd like you to watch. So after we do this brief introduction, watch that pre-lab, and then we'll head over into the lab and carry out the 14 reactions. We've been talking about double displacement reactions quite a lot in lecture, but it probably wouldn't hurt to do a bit of refresher here before you get to work on the lab. So double displacement reactions have that usual AB plus CD type of format. We've got normally two ionic compounds switching partners to form AD and CB. So let's go through a few examples. This is the reaction between palladium 4 nitrate and sodium carbonate. Palladium has a +4 charge and carbonate is a -2, so we'll get 1 palladium and 2 carbonates. Sodium, of course, is a +1, nitrate is a -1, and therefore NaNO3 would be our other product. We also need to balance the equation. We have 4 nitrates over on the left side, which means we will need 4 sodium nitrates. And now that we have 4 sodiums, we'll need 2 sodium carbonates, and we have 1 palladium on each side, 2 carbonates. Everything is balanced. And finally, of course, we need to know the physical states if we're going to predict whether a reaction occurs. So using our solubility rules, nitrate having a charge of -1 tells us palladium 4 nitrate will be aqueous. Sodium has a charge of +1, so sodium carbonate is aqueous. However, palladium at +4 and carbonate as a -2, we would predict that that compound will be insoluble and therefore will form a solid precipitate. The 95% rule says if both ions have a charge greater than 1, then we'd expect it to be insoluble, and it is. And finally, of course, sodium nitrate, both ions have a charge of 1, therefore that compound will be soluble. This reaction, of course, is a precipitation reaction. That's one of the 3 types of reactions that you're going to see in class today. And we'll talk about the other 2 in just a moment. This particular way of writing the reaction is called the molecular equation. We don't actually have any molecules here, but as we talked about in lecture, the reason we refer to it as a molecular equation is because we're leaving the ions together rather than having them dissociate, because that's how molecules behave. This is sort of the simple way of representing the structure. Sort of like having a ball and stick diagram as opposed to a Lewis structure. It's just a simpler way to do it. Of course, any chemist would see that aqueous symbol there and realize that these ions are not actually staying together in the solution. They're going to dissociate. Any ionic compound which is aqueous is going to dissociate in water. So the more appropriate way to represent palladium 4 nitrate is to have a single palladium ion in solution and 4 individual nitrate ions. Same thing is true with the sodium carbonate. We'll end up with 4 sodium ions and 2 carbonate ions in the solution. Palladium 4 carbonate, on the other hand, we're going to leave it as it is because it's insoluble in water. So solids are going to remain intact as a crystal rather than dissociate. And of course, the sodium nitrate will dissociate into 4 sodium ions and 4 nitrate ions. This particular way of writing the equation is called the complete ionic equation. This is the most thorough way you can write the reaction. It shows every single detail in the reaction. We don't commonly write all of this out. It's a lot of work. A chemist or a chemistry student can look at the molecular equation and realize, oh, these are actually going to be separate. It's sort of like looking at a ball and stick diagram of a molecule and realizing there are actual non-bonding pairs of electrons that just haven't been shown, but we know they're there. There's also a third way that we can represent these equations, and that is by getting rid of what are known as spectator ions. For example, we have 4 nitrates on the left side of the equation and 4 nitrates on the right. So as we would do in an algebra problem, we can simply cancel those out. So we can get rid of the 4 nitrates on the left and get rid of the 4 nitrates on the right. The same thing is true with the sodium. We have 4 sodiums on the left side, and we've got 4 sodiums on the right. The nitrate and the sodium atoms did not change during the course of the reaction. That's why they're referred to as spectator ions. They're not actually participating in the reaction. They are simply watching what's going on. On the other hand, the palladium and the carbonate are reacting. So our palladium ion and our carbonate ion are coming together to form palladium carbonate. So we're going to leave the palladium and we'll leave the carbonate and simply show the palladium 4 carbonate product. This is a much simpler way to represent the reaction. This particular type of reaction is called a net ionic equation. It's sort of the net result you get once you get rid of all these spectator ions. So the net ionic equation essentially just shows the ions that are participating in the reaction, and it leaves out those spectator ions. Spectator ions are important, of course, because the palladium and the carbonate couldn't have gotten together if they hadn't come with the sodium and the nitrate. It's sort of like going to a dance. I mean, palladium needed a date, that was nitrate, and carbonate needed a date, that was sodium. But once they got to the dance, they dumped their partners and they got together with each other. It's also possible to have a double displacement reaction that doesn't include 2 ionic compounds. We can also have an acid, which is a covalent compound. In this particular case, we have sulfuric acid reacting with potassium hydroxide. And you probably realize, oh, that's an acid and that's a base. And we talked about that in lecture as well, acid-base reactions. When an acid and base react with each other, the positive ion from the base gets together with the negative ion from the acid to form an ionic compound, and the hydrogen ions and hydroxide ions simply come together to form water. To balance the equation, in an acid-base reaction, it's very simple. All you need to do is make sure the number of H's and OH's and H2O's are all the same. We had 2 hydrogen ions in sulfuric acid, so we need 2 potassium hydroxides, and we'll get 2 water molecules. We'll also want to label the physical states. Acids are always aqueous. Potassium, being a charge of 1, potassium hydroxide will be aqueous. Potassium sulfate, again with potassium present, will be aqueous. And water, of course, is a liquid because water is the solvent in which the reaction is taking place. This, of course, is an acid-base reaction. That's the second type of reaction that you will see in the lab today. Of the 14 reactions that you'll be carrying out, some of them will form precipitates, some will be acid-base reactions. The acid-base reactions are the easiest to recognize because you have to have an acid and a base. And in today's lab, all of the acids begin with hydrogen, all of the bases end with hydroxide. There's also a third possibility today. You may mix together 2 ionic compounds and then form your 2 new compounds, yet find out that all 4 substances are aqueous. If they're all aqueous, that means nothing happened. If we didn't get a precipitate, we didn't have a precipitation reaction. If we don't have an acid and a base, we didn't have an acid-base reaction. So some of the reactions today will be no reaction. So of those 14, there will be some of each of those 3 types. Now keep in mind that the acid-base reactions, like the no reactions, will not necessarily show you any great sign that a reaction took place. With an acid-base reaction, since we're not getting a precipitate, you're not going to see any change in the liquid. You may notice that the test tube becomes warmer. Acids and bases tend to produce a lot of heat when they react with each other. If you feel the test tube, you may well feel that it gets warmer, and you may also notice a bit of fog or steam at the surface of the liquid in the test tube, which is caused by that heat. With the no reaction, you're going to see no reaction. There'll be no temperature change, no precipitate, no color change, no nothing. So just to summarize then, you'll have 3 different possibilities in today's experiment. The first one, of course, was precipitation, and we'll know we have a precipitation reaction if one of the products is insoluble in water. Our second possibility is an acid-base reaction, and even though there may be no visible signs that a reaction took place, remember what we said in class, acids and bases always react. So whether you see anything happen or not, if your reactants are an acid and a base, you're going to predict a reaction will take place and you will be correct. And of course, our third possibility was no reaction. If all 4 substances are aqueous and it's not an acid and a base, then we will have no reaction. So what do we need to do before starting the lab? In order to identify precipitation reactions, that's all based on solubility. You need to be able to predict whether a substance will be soluble or insoluble in water. So I would like you to complete this table. There's a list here of various ionic compounds. I want you to use the solubility rules that we talked about in class, and they're also on page 3 of the experiment. Apply those solubility rules and see if you can predict the solubility of each of these compounds, whether it's soluble or insoluble. This is just for practice, so once you've done that, you'll find later in the experiment there's a list of all of the correct answers for this and why. But it's good practice for you so that you'll be able to do a good job in the experiment. Now these are the 14 reactions that you'll be carrying out. For each of these 14, you need to predict what's going to happen. The best way to do that is to go ahead and write out each of those 14 reactions. The molecular equations, balance them, label the physical states, and you'll be able to tell from that whether it's an acid-base reaction, a precipitation reaction, or no reaction. Question number 1 at the end of the lab actually asks you to write out the molecular equation for all 14 of these, so if you do that now, you'll be ahead of the game at the end. And then finally, before beginning the lab and looking at the actual reactions, I would like you to predict what you think is going to happen. So after you've written out those 14 reactions, you should be able to predict yes or no whether you think a reaction is going to take place. Then we'll head on into the lab and you can record the observations for each of these 14 and then list the results over here, yes or no again. In a perfect world, ideally, all of your 14 predictions will match the 14 results. It's rare for a student to get all of those, but if you follow the solubility rules religiously and you watch to see if you have acids and bases in the reaction, you should be able to do a very good job of making those predictions. So on that note, let's head on over to the lab and start looking at the actual results for each of those 14 reactions. All right, this is reaction number 1 for experiment 10. So first we'll add the 0.1 m sodium chloride. And then we'll add to that the silver nitrate solution. And very quickly you see that it forms a nice white precipitate. All right, this is reaction number 2. All right, this is reaction number 2 for experiment number 10. First, we'll add a little bit of sodium carbonate. And then we'll add to that some calcium chloride. And we very quickly, once again, get a nice white precipitate. All right, this is reaction number 3 for experiment 10. First, we're going to add some sodium hydroxide. And then we'll add to that some hydrochloric acid. Now you'll notice this time we don't actually see a precipitate forming, but remember, acids and bases always react. And if we feel the test tube, ooh, it's very warm, so you can tell the reaction's happening because there's a lot of heat being given off. This is reaction 4 for experiment 10. So first, we'll add some potassium nitrate. And then some calcium chloride. And you'll notice this time there doesn't seem to be any evidence of a precipitate. And if we feel the test tube, there's no heat as well. So sometimes there's simply no reaction. This is reaction number 5 for experiment 10. First, we'll add some of this blue copper sulfate solution. And then we'll add to that some of our sodium hydroxide. And you notice it looks sort of like a blue gel. It's still a precipitate. Sometimes people say it looks sort of like blue snot. This is reaction number 6 for experiment 10. So first we'll add some zinc nitrate. This is actually zinc 2 nitrate, so when you're balancing the equation, it's a positive 2. And then we'll add to that some sodium phosphate. And once again, you can see a nice white precipitate is forming. This is reaction number 7 for experiment 10. So first, we'll add some barium chloride. And then we'll add to that some sulfuric acid. Ooh, and get a really quick precipitate that time. This is reaction number 8 for experiment 10. So first we're going to add some silver nitrate. And then we'll add to that some hydrochloric acid. And get a very intense precipitation reaction. This is reaction number 9 for experiment 10. First, we're going to add some ammonium hydroxide. And then we'll add to that some nitric acid. And this time you see no evidence of any precipitate, but if we feel the test tube, Ooh, it feels nice and warm, and you can probably see the steam sort of rising above the liquid because acids and bases always react. This is reaction number 10 for experiment 10. So first, we're going to add some calcium chloride. And then I've made one small change. Instead of ammonium hydroxide this time, we're using sodium hydroxide. So when you balance the equation, make sure you substitute the sodium hydroxide. And you can see we get a nice white precipitate very quickly. This is reaction number 11 for experiment 10. So first we'll add some iron chloride, which is sort of a pale orange color. And then we'll add to that some sodium carbonate. And we get a very pretty orange precipitate. This is reaction number 12 from experiment 10. So first we'll add some zinc nitrate, and remember again it's zinc 2 or zinc plus 2 nitrate. And then we'll add to that some sulfuric acid. And there doesn't appear to be any sign of a precipitation occurring. And if we feel the test tube, it is completely cool. So it looks like no reaction in this case. This is reaction number 13 from experiment 10. So first, we'll add some potassium nitrate. And then to that, we'll add some sodium phosphate. And it appears that there's no precipitate forming here. And if we feel the test tube, it's perfectly cool, so it looks like no reaction. This is reaction number 14 from experiment 10. So first we'll add some copper sulfate. And then to that we'll add some sodium phosphate. And we get a really pretty blue precipitate. This concludes all 14 reactions for experiment 10. You should now have all of the data that you need to go ahead and complete the experiment.